Our second item for today is called exponential decay. So again, I want you to think about a specific example. This time, let's go ahead and think about a geology class. So I'm going to walk in and I have a big rock in my hand, but this rock happens to be uranium. Now, as you think about uranium, uranium is a radioactive element. So as it's sitting there, what's going to happen is that little radioactive parts are going to be scattered throughout the room as you are watching this lump of uranium. And if you think about how radioactive that uranium is, when you first look at it, it's going to be radioactive, and then a little bit later it's going to be a little bit less radioactive, and then it's just going to keep on going down from there. So on exponential decay, we're going to be looking at problems where you start at the highest and then you go down from there. So you'll see that we have a graph here. Let's go ahead and see what this graph looks like. So we'll start off with an initial amount of radioactive material, and then we're going to go downhill from there. Now, it's interesting to note then that, again, we're going to be looking at part of an exponential function. And as you look at this graph, this time we're going to see that the horizontal asymptote is going to kick in. Because eventually, if we think about that radioactive material, we're going to get to a point where it's no longer radioactive. So we're going to get closer and closer and closer to this idea of zero for the amount of radioactive material. And again, because it's an exponential function, we can write that as a of t is equal to a sub 0 e to the kt. Now, as you look at this, you're going to notice that the letter has changed here. Really, when the author makes that choice of saying that this is A, he's just saying that it's the amount of radioactive material. But truthfully, it is the same formula that we were looking at a moment ago for exponential growth. So if you look at this and you think about it in terms of n's instead of a's, it doesn't really matter. So if you want to just memorize one formula and say that it works for both exponential growth and exponential decay, you're certainly welcome to do that. Here, I'll go ahead and use the A's simply because the author does. But again, the letter there, I could use N and it could be just fine as well. So what is the biggest thing then that is different when you're looking at an exponential decay problem instead of an exponential growth? It's this K value. K is now going to be not a growth rate, but a rate of decay. And K then is going to be a negative number, and that's why then we're going to be going downhill like we're looking at this problem.